So hello everybody, we are dealing with a very interesting problem, and this problem will be dealing with a lot of concept of circular motion, Newton's law, combining the ideas of friction. Then we'll be breaking the component of force, thinking about angle of repose. So it is a multiple concept problem, and the problem is stating a disk of radius capital R inclined at an angle theta with the horizontal is evenly covered with a thin layer of sand. Coefficient of friction between the sand and the disk is mu. The disk is made to rotate about its central axis of symmetry with gradually increasing angular velocity. The angular velocity is increased so gradually that tangential acceleration of any of the sand particle is practically negligible. What is the angular velocity of the disk when eta fraction of the sand has fallen off the disk? Consider acceleration due to gravity to be g. So there is a lot of information which is provided in the problem, and we are going to use them eventually to our cause. So let us start by drawing a necessary arrangement. So this is the necessary arrangement which we have, and obviously in this current diagram I am not drawing it in the way that the disk is inclined. So we are right now understanding why exactly the sand will fall off. So over here, let us consider that if we are talking about a sand particle of mass m, which is at a distance r from the axis of rotation of this disk, then what is going to happen to this particular point mass m which we have selected? So this point mass is going to be subjected to a force which is given by m omega square r, and due to this force, this sand particle will try or will have a tendency to leave this particular plate or disk on which this mass is placed. So over here, one thing to understand is this, that if radius increases, the force which is m omega square r will also increase, and we can say that the particles on the periphery of the disk will have more tendency to fall or fly off when the disk is rotated with an angular velocity omega. So this is the first aspect that we need to understand. Now in the problem, the disk is also given an incline or inclination theta. We are coming to that. Before that, let us see, or let us consider that initially the entire disk was covered with sand covering a radius capital R, and now we are considering that if the sand remains only till a radius small r, then what is the fraction of the sand removed? So if we do this calculation, so we are saying that the removed sand, or technically we can say removed sand area or layer, then we are saying that it was initially pi r square and now only pi r square is left. So we say that pi r square minus r square is the value of sand area removed, and if we consider the original sand cover or sand area, then it was equal to pi r square. So if we consider the fraction of the sand removed, or eta, then eta can be written as pi r square minus r square by pi r square. So this is the fraction of sand that is removed. We can remove pi and then we can write this term as 1 minus r square by r square. So over here, if we wish to write small r in terms of eta, then small r in terms of eta can also be written as r square by r square is equal to 1 minus eta, and hence over here we can say that small r is equal to capital R square root of 1 minus eta. So we will be using this result in the further aspects of the problem, so that is why we have evaluated it so far. Now we are coming to the inclined part. So on inclination, what is exactly going to happen? That an additional force down the incline mg sine theta will also act, and as a result of which the sand layer will have a tendency to slip off the surface due to two forces involved, m omega square r and mg sine theta. And the force coming to its rescue will be frictional force, which will originate because of the normal reaction force. So if we consider the part when we are inclining this surface, so we are looking at a part like this. So now over here, if we draw the FBD at the tip over here, because this is the portion which is not falling off, so this is the limiting case. So we are saying that the weight of this particle must be mg in the downward direction. Now the component of weight mg will act in this direction. It will be written as mg cos theta. Another component will be acting down the incline. This is mg sin theta. A component of normal reaction force will act up the incline. And now because of the sense of rotation, a force m omega square will act in this direction. Now one important aspect about this m omega square r is that this force will have no component in the direction of mg cos theta, as this angle is 90 degree. So there will be no component of m omega square r in this direction, so it will not change the normal reaction force. And then in order to prevent slippage, the friction force will come into act. So now if we equate the value of forces in the direction of normal reaction force, so we say normal reaction force nr, then it is equal to mg cos theta, and the value of friction force will eventually become mu mg cos theta. And now if we equate the forces along the incline, so we say forces acting down the incline are mg sin theta, and followed by mg sin theta we have another force m omega square r, and they are balanced by frictional force mu mg cos theta. So these are the forces which is acting down the incline, and from here if we solve for omega, so we get omega equals g by r mu cos theta minus sin theta. So g by r mu cos theta minus sin theta square root. So now if we substitute the value of r over here in this expression, then we get the value of omega which we are looking for, which is equal to g mu cos theta minus sin theta by r root under 1 minus eta, and this entire parameter is inside a square root. So this is the final answer which we are looking for this beautiful problem which we have solved, calculation of angular velocity omega when eta fraction of the sand has fallen out. So we have considered every small detail in this problem. We have considered that the angular velocity is increased so gradually that there is nothing about tangential acceleration of any of the sand particle. So this is the problem which we have discussed. I hope you understood the solution in a proper way. Do continue to like, share and subscribe, and continue to watch the channel for more such videos.